Hi students, today's class we learn about relations. Relations in class 12 mathematics, it is the first chapter and it is very important chapters. So relations, to know relations first, we have to know the Cartesian product of two sets. Let A and B are two sets. A and B are two sets. Then the Cartesian product of the set A and B is denoted by A cross B and is defined by A cross B equal to set of all ordered pairs. Set of all ordered pairs such that x comma y such that x belongs to A comma y belongs to B, x belongs to A and y belongs to B. That is Cartesian product of two sets. Cartesian product of two sets A and B is denoted by A cross B and is defined by set of all possible ordered pairs x comma y, ordered pair, such that the first element comes from A and the second element y comes from B. Suppose for an example, let A equals to 1, 2, 3, three elements, and B equal to A and B. A consists of 1, 2 and 3 and B consists of A and B. Then A cross B equal to set of all ordered pair 1 comma A, 1 and B. Now 2A, 2B, 2A, 2B. Now 3A, 3B, 3 and A, 3B. B cross A, then what will be? Then in this case, in each order pair, first element comes from B and second element comes from A. In this case, B cross A will be A1, A2, A3. Now B1, B2 and B3. Obviously, A cross B not equal to B cross A. 1A, A1 are not same element. It is different. 1A, A1. These two elements are not same. A consists of three elements, that is cardinal number of A is 3, and B consists of two elements 1, 2. A cross B, Cartesian product of A and B 1, 2, 3, 4, 5, 6. Cartesian product of A cross B, the cardinal number of Cartesian product of A cross B equal to 6. Obviously, 6 means 3 into 2. That is, N of A cross B equals to NA into NB. NA into NB. So, if a set A, any set, cardinal number of A equal to M, say cardinal number of B equal to N, then cardinal number of A cross B will be cardinal number of A into cardinal number of B, that is M into N. Cardinal M into N. Okay. Now A cross B, the Cartesian product of the two sets A and B is the set of all ordered pairs such that first element of the ordered pair comes from A and the second element from B. Now relation. Suppose A and B are two non-null sets, then A cross B is the Cartesian product of A and B. Now let R be a subset of A cross B. R be a subset of A cross B. Then R is said to be a relation from A to the set B. That is, any subset of A cross B, any subset of A cross B is a relation from A to B, from the set A to the set B, any subset. Then now how many elements in A cross B? In A cross B equal to NA into NB. Number of elements in A cross B, NA. Now how many subsets of A cross B are there? How many subsets? In the set theory, we know that if a set A consists of n number of elements, if a set A consists of n number of elements, then the number of subsets of A, number of subsets of A equal to 2 power n, that is 2 power Na, 2 power n. So number of elements of A cross B equal to Na into Nb. Then number of subsets of A cross B, number of subsets of A cross B equal to 2 power this, 2 power Na into Nb, 2 power Na into Nb. This is the number of relations. Because every subset of A cross B is a relation, that is, number of subset of A cross B, this equals to number of relations. Then if a set A consists of 3 elements and the set B consists of 2 elements, then the number of relation will be, suppose NA equal to 3 and NB equal to 2, then number of relations from A to B equals to 2 power 3 into 2, 3 into 2, 2 power 6 equal to 64. Number of relation, 64 relations can be formed. For example, let A equal to 1, 2, 3, 4, 5 and B equal to P, Q, R, S. P, Q, R, S. Then RBA relations from A to B. RBA relations from A to B. Then obviously R is a subset of A cross B. R is a subset of A cross B. So let R equal to, we take first element from A and second element from B. R 1 B 2 R 3 S 4 P. In A cross B, how many elements are there in A cross B? Number of elements here is 5 and here is 4. 5 into 4, 20. That is, in A cross B there are 20 ordered pairs. We take 1, 2, 3, 4. 4 ordered pairs out of 20 ordered pairs. Obviously our subset A cross B. Every ordered pair, this belongs to A cross B. A cross B contains 20 ordered pairs. 5 into 4. 5 number of elements, 4 number 5 into 4. That is 20 ordered pairs. Out of 20 ordered pairs, we take only 4 ordered pairs. So R is a subset of A cross B. R is a subset of A cross B. So R is a relations. So this is a relations. This is a relations from A to B. A to B. A to B. Then the domain of these relations is denoted by domain R. Domain of the relations is the set of the first elements 1, 2, 3, 4. First element contains, that is pre-images 1, 2, 3, 4 domain. And range of the relations are, range means the set of images P, Q, S, P. P repeats twice. So P, R, S, distinct element P, R, S. P, R, S. We take P once, not twice. Because P, same element. If there is a same element, you will take one P, because in a set, every element are distinct, no element repeat. So range P, R, S, domain 1, 2, 3, 4. Actually, domain means domain of any relation R, means set of all x such that x comma y belongs to R. For every ordered pair belongs to R, the set of first element means this is P, this is called T image, and Y is called image. Y is called image, and X is called pre-image. In these relations, P is the image of 1, 1 is the pre-image of P, 2, R is the image of 2, 2 is the pre-image of R. Similarly, S is the image of 3, 3 is the pre-image of S, like this. And range means range of R equals to set of all y such that x comma y belongs to R. X comma y belongs to R. This is the range. So relations, domain and range. Now, the inverse of a relations. Let A and B are two non-empty sets. A and B are two non-empty sets, and A cross B is their Cartesian product. Let R subset of A cross B, then R is a relations from A to B. R is a relations from A to B. The inverse relations of R. The inverse relations of R is denoted by R inverse. The inverse relations of R is denoted by R inverse and is defined by set of all y comma x such that x comma y belongs to R. X comma y, if x comma y belongs to R, then y comma x belongs to R inverse. Suppose R is a relations on the set A equals to 1, 2, 3, 4, 5, B equal to P, Q, R, and R is the relations from A to B, 1, P, 2, Q, 3, R, 4, R. This is the relations from A to B. Then R inverse will be obviously 1P here, P1, 2Q, for 2Q we have to take Q2, 3R, R3, 4R, R4. This is the inverse relations. R is the relations from A to B, Then R inverse, first element comes from B and second element comes from A. Then R inverse is the relations from B to A to B. This is set B. If this is R, then R inverse is from B to A. That is, domain of R is range of R inverse, and the range of R is domain of R inverse. Interchange. Domain of R means 1, 2, 3, 4. Range of R inverse second element 1, 2, 3, 4. Again, range of R P, Q, R. Domain of R inverse P, Q, R. I repeat twice, take 1 times. P, Q, R. So, inverse relations. Now, three types of relations. Number 1, reflexive relation. Number 2, symmetric relation. Number 3, transitive relation. Reflexive relation. Suppose R is, to do this we have to know the relations on the set A. Relations on the set A. So let, if R is a subset of A cross A for any non-empty subset set A be a non-empty set, R is a subset of A cross A, then R is a relations from A to A. R is a relations from A to A. R is a relation from A to A, but we do not say that. We say R is a relations on the set A. R is a relation on the set A. In this case, the domain and codomain both are same. Then we say R is a relations on the set A. R is a relations on the set A. Now suppose R is a relations on the set A is a relation on the set A. Then R is reflexive. R is said to be reflexive if A, A belongs to R, or all A belongs to A. For all A belongs to A, A, belongs to R. That is, A is related to A is related to A. For all A belongs to A, then R is said to be reflexive relations. Reflexive relations. For example, let A equals to 1, 2, 3, 4, 5. In this set, we have defined relations 1, 1, 2, 2, R1. 1, 1, 2, 2, 3, 3, 4, 4, 4, 5. This is a relation 5, 3. This is a relations R1. R2 is another relations 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 3, 2. Then, which is reflexive relations? R1 or R2? First observe R1. For all A belongs to A. For all A. For all A means 1. For 1, 1, 1. A. For 2, 2, 2. For 3, 3, 3. For 4, 4, 4. For 5, 5, 5. There is no 5, 5. So it is not reflexive. It is not reflexive because 5, 5 is not here. 5, 5 does not belongs to R1. So it is not reflexive. This 1, 1, 1, 1, 1, for 2, 2, 2, for 3, 3, 3, for 4, 4, 4, for 5, 5, 5. All are exist. We then 3, 2, 3, 2 is we have to only observe that A belongs to R. Other elements we not found. Other elements may exist or not, may consist or not. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. This condition is satisfied. For all A belongs to A, A belongs to R. So we have to just see this. So this is reflexive relations. Now transitive relation. Symmetric relations. A relations on the set A, not A to B, on the set A. A relations R is a relations on the set A, R is a relations on the set A. So R is said to be symmetric. R is said to be symmetric if for all A, B belongs to R, imply B, A also belongs to R. If A, B belongs to R, then B, A also belongs to R. This is symmetric. Suppose A equals to 1, 2, 3, 4. R is a relations on these sets 1, 1, 2, 2, 3, 3, 4, 4, 2, 3, 3, 2, 1, 4, 4, 1. This is symmetric or not? If AB belongs to R, then BA belongs to R. So 2 3 belongs to R. 3 2. 1 4 4 1. 1 1 reverse is 1 1. 2 2 reverse is 2 2. 3 3 reverse is 3 3. 4 4 reverse is 4 4. 2 3 3 2. 1 4 4 1. So it is symmetric. Now transitive relation. Transitive relation. R is the relations on the set A. Same. R is the relations on the set A. Then R is said to be transitive. R is said to be transitive. R is said to be transitive if A related to B, also B related to C, then A related to C. That is, if A comma B belongs to R, B comma C belongs to R, then A comma C belongs to R. This is transitive relations. One example. You take another example. Let A be the set of natural numbers. Natural numbers less than 6. That is, A is 1, 2, 3, 4, 5. And R is a relations defined on A such that R is the set of all x, y such that x less than y. X, y belongs to A. Then obviously R is x less than y. Then we can take 1, 2, 1, 3, 1, 4, 1, 5. 1, 2, 1, 3, 1 less than 3. 1, 4, 1, 5. And 2, 1. No, 2, 1, 2 not less than 1. 2, 3. 2, 3, 2, 4, 2, 5. And 3. 3, 4, 3, 5. 3 less than 4. 3 less than 5. And 4, 5. 4, 5. This is transitive because 1, 2, 2, 3, 1, 3. I say 1, 3, 1, 3. 1 related to 2, 2 related to 3, 1 related to 2, 2 also related to 3, then 1, 3, 1, 3. 1 related to 3, 3 related to 4, then 1, 4, 1, 4. 1 related to 4, 4 related to 5, then 1, 5, 1, 5. So it is obviously x less than y, x less than y, y less than z, then x less than z. This is transitive relations. Now, equivalence relations, very important. Equivalence relations. A relation on the set R, on the set A. A relations R on the set A is said to be equivalence if it is reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. If a relations is reflexive, symmetric, transitive, then this relations is called equivalence relations. To show a relations, equivalence relations, we have to prove it is reflexive, symmetric, and transitive. If when a relation is reflexive, symmetric, and transitive, then it is called equivalence relations. Equivalence relations. Now we give an example. On the set of, suppose on the set of integers, integers means set of integers, on the set of integers z, on the set of integer z, the relations R is defined. The relations R is defined by R equals to set of all xy, such that x is congruent to y modulo n. xy belongs to R. xy belongs to, sorry, z. X is congruent to y. This relation is called x is congruent to y modulo n. Congruent to y modulo n. This means x is congruent to y modulo n. This means x minus y is divisible. X is congruent to y modulo x minus y is divisible by n. X minus y is divisible by n. X minus y is divisible by n. Now, this means this. Now, we have to show that R is an equivalence relation. To show R an equivalence relation, we have to show that R is reflexive, symmetric and transitive. Reflexive, symmetric and transitive. So, reflexivity for all A belongs to Z imply A comma A belongs to R. Why? Since A minus A, x minus y, A minus A, that is 0, which is divisible, 0 is divisible by any number, which is divisible by n. Therefore, A is congruent to A modulo n. So, A is related to A for every A belongs to Z. A minus A, that is 0, is divisible by n. So, it is reflexive. R is reflexive. Now, symmetricity. Now, R is reflexive. Now, symmetricity. Symmetricity means let A comma B belongs to Z. A comma B belongs to Z. This implies A is congruent to B modulo n. This implies A minus B is divisible by n. Divisible by n means multiple of n. Kn, suppose k is integer. This means b minus a equals to minus k into n. If k is integer, then minus k is also integer. B minus a, multiplying both sides by minus. This means b minus a is divisible by n. That is, b is congruent to a. congruent to A modulo N. Congruent to, that is imply B comma A belongs to R. That is, if A comma B belongs to R, if A comma B belongs to R, then B comma A belongs to R. If A comma B belongs to R, then B comma A belongs to R. So R is symmetric. R is symmetric. Now, transitivity. Transitivity let A comma B belongs to R, B comma C belongs to R. We have to show that A comma C belongs to R. A comma B belongs to R. This means A minus B is divisible by N. Is divisible by N means K1N. B related to C, then B is congruent to C modulo N, then B minus C is divisible by N, suppose K2N, where K1, K2 belongs to Z. Now if we add these two, A minus B equals to K1N, B minus C equals to K2N, plus minus B plus cancel, then A minus C equals to K1 plus K2N. This implies A minus C is divisible by N. Divisible by N. That is, A is congruent to C modulo N. That is, A is congruent to C modulo N. Therefore, A comma C belongs to R. Therefore, R is transitive. Now, since R is reflexive, symmetric and transitive, so it is an equivalence relations. So, okay, thanks.